This research paper discusses the theory of ring afterglows, which are expanding relativistic outflows that may be responsible for a variety of astrophysical transients, including gamma-ray bursts, GRBs, X-ray flashes, XRFs, superluminous supernovae, SLSNE, transrelativistic supernovae, and fast blue optical transients, FBOTs. The authors argue that while many GRBs are thought to be caused by jetted relativistic outflows, not all GRBs are necessarily jet-like, and they propose ring-like geometries as an alternative explanation. The paper begins by outlining the mathematical formalism for the dynamics and synchrotron radiation from a relativistic ring. The kinetic energy of the expanding blast wave is described by the equation E equals 2ma cubed k, 2r cubed k, where m is the swept-up mass, a is the mass-loading parameter, and k is a parameter that describes the density of the surrounding medium. The authors also derive the Lorentz factor as a function of observer time for the rain, which is given by gamma proportional t caret 1/2 equals 1 plus 2 eta caret 1/2, where eta is a parameter related to the geometry of the outflow. The paper then turns to the calculation of the synchrotron spectrum in the observer frame, which is a critical component of the theory of ring afterglows. The characteristic peak frequency of the electrons is given by nu_m equals E squared epsilon underscore EB underscore 0, 16 pi m underscore EC, where epsilon underscore E is the electron Lorentz factor, B underscore 0 is the magnetic field in the fluid frame, and m underscore E is the electron mass. The authors also note that the magnetic field in the downstream transforms from the usual jump condition B underscore 0 equals epsilon underscore B, 32 pi epsilon, caret 1/2, where epsilon underscore B is the fraction of total energy density due to magnetic fields, and the minimum Lorentz factor of the electrons obeys epsilon underscore E proportional gamma. In a time t underscore 0, the electrons cool at a rate given by t underscore cool equals 6 pi m underscore EC, sigma underscore TB underscore 0 to the power of 2 epsilon underscore E squared, where sigma underscore T is the Thomson cross-section. The authors go on to describe the observational signatures of ring afterglows, including their light curves and spectra. They show that ring afterglows decay faster than spherical outflows but not as fast as jets, and that the distinguishing features of these geometries are discernible in the current GRB catalog. The paper concludes by discussing the implications of their work, which could help explain a wide array of astrophysical transients, and by highlighting the need for further research into the physics of expanding relativistic rings. The research focuses on the temporal evolution of relativistic rings in the context of gamma-ray burst afterglows. The authors considered two types of asymmetric geometries: conical, jet-like outflows along the poles of the source and ring-like outflows in the equatorial plane. They derived the cooling Lorentz factor and cooling frequency, which are essential for calculating the spectral flux from a radiating blast wave. The authors then compute light curves for a constant density medium, comparing the results with spherical and jet-like geometries. They find that the light curves exhibit distinct features, such as differences in cooling breaks and decay slopes, which can be used to distinguish between relativistic rings and jets. The ring afterglows possess two distinct cooling breaks, similar to those calculated for spherical outflows. The authors show that the spectral flux below the self-absorption frequency and in the intermediate range between the self-absorption and characteristic frequencies follows specific scaling laws, which depend on the geometry of the outflow. At high frequencies, the light curves follow different power law decays, depending on whether the electrons are cooling or not. The results demonstrate that ring afterglows have shallower decay slopes than jets throughout their evolution, making it possible to distinguish between the two geometries. The authors conclude that the temporal evolution of ring afterglows is clearly distinct from their spherical and jet-like counterparts, which can be used to explain observations that are difficult to reconcile with the jet framework. The implications of these findings are discussed in the context of gamma-ray burst observations, highlighting the potential of ring geometries to explain shallow breaks in light curves. Expanding relativistic rings offer an alternative to jet models in explaining gamma-ray burst (GRB) light curves. A comparison of light curves from spherical, ring-like, and jet-like blast waves reveals distinct slopes in different frequency bands, particularly in the low-frequency radio and high-frequency optical, X-ray bands. Figure 2 illustrates these light curves, demonstrating the break times and frequency evolution. A recent GRB 221009A, is re-examined, and its light curve is found to be consistent with a broken power law model. The shallow decay index in the X-ray band can be accounted for by ring geometries rather than a simple top-hat jet model. Rings also have a higher probability of being viewed, as they cover a larger portion of the sky. Moreover, they do not require a complex central engine and have a more stable late-time evolution. Astrophysical transients sourced from expanding relativistic rings may provide an alternative to jets, allowing for shallow breaks and structured emission. Inverse Compton emission can also be included, extending the work to higher frequencies. Ring-like outflows are worth considering when interpreting observations of non-spherical explosions. Notably, surface brightness is no longer symmetric around the line of sight, and this anisotropy can act as a useful probe for ring dynamics. While this study focused on synchrotron emission in GRBs, its results are relevant to other astrophysical transients with non-spherical outflows. Rings preserve beaming, accounting for shallow breaks, and their unique features, including unidimensional spreading and asymmetric surface brightness, provide an interesting probe for their dynamics. Asymmetric surface brightness may also help distinguish rings from jets through the analysis of scintillation patterns. Finally, incorporating inverse Compton emission in a similar way to previous works, e.g., Sari and Eason, 2001. Nakar et al. 2009, is crucial for further analysis, as is extending these results to higher frequencies. Investigating relativistic ring geometries may uncover alternative interpretations of various astrophysical phenomena and should be explored in more depth in future research.